If you look up during the night, you will see tiny little specks of white light. And during the day, you will see the sun. These are all stars. During this presentation, I will explain to you how stars are formed, the process of which they're going through, why stars don't immediately explode or implode, and how giant stars are formed.
This picture can be found on page 280 of our textbooks, Discovering the Essential Universe, 5th edition, by Neil Comins. This is a great picture because it goes through each process of how stars are formed. In this picture in the top left, this is the nebula. This is a large body of gas and dust. This gas and dust can be found everywhere in space. Um, Between each star, there is an interstellar medium, and this is basically what it makes up, is gas and dust. And when we look through telescopes, this is roughly 10% of what we see most of the time. The compounds on this gas and dust are hydrogen, carbon monoxide, carbon dioxide, water, ammonia, and formaldehyde. These are the majority of the compounds that you can find in nebulas. Of course, there are other compounds that you can find as well, such as iron. In the center of the nebula is the densest part of the nebula. This is the birthplace of our star. The process of a star begins to form when the inner region of the nebula falls rapidly into a dense core. The outer core is pulled in as well, but at a much slower rate. This is called accretion. The center of the star is called a protostar. In order for the process of accretion to become a protostar, the center of the star needs to reach 17 to 18 million degrees Fahrenheit. Now, how this reaches such a high rate and temperature, the gases being pulled into the core try to expand as they're heating up. Although they're being pushed out because of the temperature, the gravity pulls it back inwards. This causes friction and causes the star to heat up into a protostar. This is a picture of a pre-main sequence star. This is when accretion stops, which is basically the growth of the star or adding on additional layers. This is because it increases to 17 to 18 million degrees Fahrenheit and it blows away all the dust and ice. To the left of this is the Titarian stage, which is 10 million years old. This represents low-mass sequence stars, such as our Sun. These stars are burning hydrogen and they emit strong solar winds. This causes them to be unstable. The first Titarian was discovered by John Russell Hind, and back in 1852. He thought when he saw one, he was looking for another star, but actually it was just because the star that he was observing was blowing solar winds away from it. In the bottom right, this is a main sequence star. This is currently what our sun is, and what majority of the stars are. Most stars live their lives for about 90% of their time in this stage. Depending on how big their mass is, depends on the length of which they stay within this stage. This is due to the amount of energy the star burns through. In this stage, the star can burn hydrogen. Once it's completed, well, it starts to burn helium, and this is when things become interesting because it increases its size because it begins to have two energy sources. The next picture is showing you a display of you can see currently what our mass is. It's just one, a sun, and some stars can well it can be quite large in mass and temperature, and also increasing in size. Well, the time and years it spends in this life cycle is a lot smaller. To give you an idea how big a star can be, this is a picture of UI Scuti versus our sun. And as you can tell, UI Scuti is much larger. Of course, in this stage, UI Scuti is it's burning helium and it's becoming a super hyper massive star. Because when it first started this life cycle, its mass was between 25 to 40 times our sun. Since then, it's probably burned through like half of that. To give you an idea how big this star is, it's about 5 billion times the volume of our sun, and the radius of it is 1,708 solar radii. One solar radii is the size of our sun. So this is 1,708 times bigger in radius. And also to give you another idea, the radius between our Earth and the Sun is 1 AU, which is the distance between our Earth and the Sun. The radius is 15.9 AU, or 2.4 billion kilometers. If this sun was in our galaxy, it would be touching Uranus. To give you a better idea how big UI Scuti is, I'm a visual person, so I like to visualize
these stars can get. This is the sun, mandarin. Being that we don't really have that many props in our household, I'm going to use spinach for the planets. We got Mercury, Venus, Earth, Mars, Jupiter, make that a little bit bigger, Saturn, Uranus, and Neptune. So, I mean, that's a decent amount of length, and to give you an idea how big this is, and I don't really have a prop that's big enough and circle, I'm going to use a suitcase to give you an idea how big this star is. So, if we put U, Y, Scotty in this universe, our solar system, it would be, let's see, this is Jupiter, be about that big. It would, yeah, our entire solar system would be out of whack. I hope this gives you an idea how big this planet is, and I hope I gave you a good demonstration of how planets are formed. They started with a nebula, which is a giant cloud of dust, and when the outer force pushes upon it, it causes it to spin, and this causes, it creates a dense core, and it slowly builds up into a star, or a protostar, and after a while, once it heats up, it actually creates a pre-main sequence star. And this is about 10 million years in the life of the star. And after that, it became stable, and then that's when our stars, 90% of their life is the main sequence star. I hope that helped you understand how stars are born, and